integrated MSc third year, and I am presenting an experiment before you from the course Applied Instrumentation PHN 310. So the experiment we are going to perform today is speed measurement using electromagnetic pickup. So for the apparatus we have here this kit, this trainer, and in here we have this power supply, and from power supply the supply goes to this motor. This motor rotates the disc and it generates an electromagnetic signal in this sensor, which transmits the output to this oscilloscope, which converts this wave shaper, and it converts the signal, the generated signal, into a perfect square wave, which transmits the data to this oscilloscope, and which calculates the frequency of the generated signal, and we are able to get the speed of the rotating disc. Okay, so what's the working principle of this setup? So as you can see here, this is a motor. When it rotates, the tooth, when in front of the sensor there is a tooth that is a magnetic material, this LED lights up and it outputs a 5 volt, that is high voltage, high logic. Okay, and when there is no tooth, there is an air gap, then this sensor outputs 0 voltage. So by the stream of these ones and zeros, we can calculate the number of pulses that are generated by this sensor, and count by multiplying it with a suitable factor, we can get the RPM and the speed of the rotating disc. You can see here, this is a rotating disc, these are the tooths, these are the teeth, and this is the air gap. This is the electromagnetic sensor. When there is tooth in the proximity of the electromagnetic sensor, this sensor outputs 5 volt, and when there is an air gap in the proximity of the electromagnetic sensor, it outputs 0 volt. And this is the kind of wave, that is induced voltage, that is generated by the electromagnetic sensor, which starts from 0 volt, it goes up to 5 volt, and then it decreases to 0 volt and then 5 volt, and so on. The output of this electromagnetic sensor is fed into a wave shaper, which shapes the wave into a perfect square wave, and which is fed into the oscilloscope to determine the frequency of the oscillating wave. Now coming to the observations, so we have to perform two observations. First, we have to keep the switch in the RPM position, and we have to set the supply voltage to the motor, and we have to get the frequency from the wave shaper and from the multiplier, and also from this RPM display meter, and we have to compare the results. Then what we can do is we can set this to speed, and we have to manually note the time of the observation and count the number of pulses that are generated by the electromagnetic sensor, and dividing the time taken by the observation, we can get the velocity, angular velocity of the rotating disc. So for the first case, for the RPM measurement, what we can do is we can set this supply voltage. This is motor supply voltage. We can set it to approximately 1.6 volts. Yeah. So this is 1.6 volts. Now we have connected this oscilloscope from this wave shaper. So from the oscilloscope we can get the frequency of this wave shaper. It is approximately 120 Hertz. Now if we take the measurement out of the multiplier, so this wave shaper feeds the output into the multiplier, which multiplies the incoming wave by a factor of 4, and then output it to the oscilloscope. And if we see here in the oscilloscope, the frequency that's outputted by the multiplier, it's approximately 485 Hertz. by seeing on the display meter that displays the RPM, we have 485, right? So we can take multiple reading by changing the voltage of the motor, sorry. So now we are taking it 1.7 volts approximately, and the wave shaper output is, the multiplier output is 530 hertz, and the wave shaper output is 123 hertz, and the display RPM shows 532. So continuing in this fashion, we can take multiple readings and we can compare the multiplier output and the display in RPM to note down the characteristics of this trainer. If we change the voltage to 2.0 volts approximately. The wave shaper output is 142 hertz, and the multiplier output that we get for this particular voltage is 678 hertz, and the display meter displays 679. Okay, now we change the supply voltage again to 2.4 volts. The multiplier outputs 855 hertz. The wave shaper, it's giving us how much it is. The signal is fluctuating quite a bit, but it's approximately 150, and the RPM meter gives us 858 revolutions per minute. Okay, so I guess that is enough for this particular measurement. Now we have to do another observation, which is speed pulse counter observation, and we can determine the speed from this measurement also. For this particular measurement, we have to set a particular voltage for the motor, and then we have to note down the display RPM display meter reading, and then we can toggle the switch to the now for this particular reading, we are taking the observation at 2.4 volts. The RPM meter displays 863 hertz. Now we can toggle the switch to the speed position. We can reset the counter to 0, and we can use this stopwatch to measure the time for which the counter button is pressed. So it's 3, 2, 1. Okay, sorry. Let it go for. Okay, so we have the readings. The pulses, number of pulses is 1118 as counted by the pulse counter, and the time as noted by the stopwatch is 4.72 seconds. Okay, we can take another reading at different motor voltage. Okay, so this is 1.84 volts. The RPM meter displays 601 hertz. Now we can count the number of pulses along with the time. Okay, so we have 894 pulses in 5.22 seconds. Just one more reading. It is at 1.5 volts approximately. The RPM meter displays how much? It's 393 390 hertz approximately, and the counter is at 560 pulses in 5.32 seconds. Okay, we have 15 slots in the disk, which means 15 pulses will be generated on every rotation of the disk. Okay, now if we take the output of the RPM meter, which will be the number of rotations per minute, we can calculate the angular frequency by multiplying it by 2 pi, which will give the angular velocity in radian per minute. To get the velocity at the edge of the disk, which is at the circumference, we will multiply it by the distance, the radius, that is r. So the velocity will be f times 2 pi times r. So f times pi d. D is 85 mm as we have known for this particular disk. So we will get velocity equal to f times 267.14 millimeter per minute. So these are the calculations for the value of RPM. Now to get to for the value for the calculations for the pulse counter, we can take this from this diagram. We know that there are 15 slots in the disk, so there will be the distance between the two teeth will be the circumference divided by 15. So 267 divided by 15 will be 17.8 mm. So if we know the number of pulses that are generated and the time it takes to generate those number of pulses, we can multiply it by 17.8 mm and get the velocity of the rotating disc at the circumference. Now from the second observation that we take, we can note the value of the RPM to be 862 Hz and the number of pulses are 1118 in 4.72 seconds. We can use the formula that we just discussed to calculate the velocity at the outer edge in meter per minute, which will be equal to the RPM output times 267.14 and dividing it by 1000 to convert into meter, we will get 230.2 meter per minute. Now from the pulse counter, we know that the number of pulses are 1118, dividing it by 4.72, that is the time taken, and multiplying it by the distance between two teeth will be 4216 millimeter per second. Multiplying it by 60, we will get 253.0 meter per minute. Now comparing these two values, there is significant error, and we can calculate the error for each observation that we take and formulate this table. This is for the experiment that I have performed, and in here you can see that for different multiplier output and the display RPM output, I have computed these errors, and for the speeds that I have computed from the pulse meter and from the RPM meter, I have computed the error, which comes out to be 3.882%. Okay, so today we have performed this experiment of determining the velocity of a rotating disc from electromagnetic pickup, and thank you.